Good morning. The last topic of Unit 2 is recursive algorithms. So, recursive algorithms is basically whatever algorithms you have studied in the previous subject along with recursion. So, in this topic, we will study the algorithms which are recursive in nature, and along with that, we will also see what is the difference between recursion and iteration. So, let's begin the topic. First, we are supposed to see a few algorithms which are recursive. First, let's see the definition of recursive algorithms. An algorithm is called recursive if it solves a problem by reducing it to an instance of the same problem with smaller input. Now, what does this mean? It means that when we can reduce a solution, when a solution is reduced to a problem, so the solution of a problem can be reduced with a particular set of input values, and we can get the same problem with smaller input values. That is, suppose if we have factorial of 5, f of 5, and we are supposed to find 5 factorial. Now this problem can be reduced to this another problem where we can reduce the input. So we can write it as 5 into 4 factorial. So over here the input is reduced to 4. From 5 we have taken the input as 4. Next, after that, again this 4 factorial can be reduced to 5 into 4 into 3 factorial. So each and every time we are reducing the input and we are solving the problem with a smaller input. So this is basically the definition of recursion or recursive. Now, for the algorithm to terminate, the instance of the problem must eventually be reduced to some initial case for which the solution is known. Okay, so we have supposed to keep reducing the problem till we get some initial case for n is equal to 0 or n is equal to 1, which is already defined. We have to keep solving the problem that many times until and unless we get the initial case. So this will continue till 5 into 4 into 3 into 2 factorial, and then 5 into 4 into 3 into 2 into 1 factorial, and then 1 into 0 factorial. The initial case for a factorial problem is 0 factorial, which we know 0 factorial is equal to 1. So if the Pascal triangle, if you remember, it started with 1, then again we had 1 1, then 1 2 1, and so on. So the initial case for our Pascal triangle was 0 factorial. So we have to keep on reducing the problem until we get an initial case for which the solution is known. So the next example actually is the same fact. So over here the example is, give a recursive algorithm for computing n factorial where n is a non-negative integer. So using the recursive definition, we can build a recursive algorithm. Let's see it over here. So we can build a recursive algorithm that finds n factorial where n given is a non-negative integer or it is a positive integer z plus. Now, based on the recursive definition of n factorial, we know that, so recursive definition we have already seen for n factorial, which is n into n minus 1 factorial. Okay, as I have shown you, 5 factorial will be 5 into 4 factorial, where n again is a positive integer, and the initial condition IC is equal to 0 factorial is equal to 1. The initial condition is 0 factorial is equal to 1. To find n factorial for a particular integer, we use the recursive step n times. Okay, and each time we replace this n minus 1 over here, we multiply it n into n minus 1 and replace it with n minus 2, and this continues till we get last step, we insert the value of 0 factorial. So the recursive algorithm is written as follows. So over here we take, for example, if we want to find the 4 factorial, or we can even take the 5 factorial example, first we are supposed to use the recursive step. So 4 factorial will be written as 4 into n minus 1, 3 factorial. After that, 3 factorial, we have to write 3 factorial is written as 3 into 2 factorial, and this is substituted over here. So this 3 into 2 factorial will be substituted. Then 2 factorial will be written as 2 into 1 factorial. 2 factorial will be substituted over here. then 1 factorial is written as 0 into, over here we will have 1 factorial will be 1 into 0 factorial, and 0 factorial value is known as 1. So this can be written in the following way. 4 into 3 factorial, already it is given. 3 factorial can be replaced by this, 4 into 3 into 2 factorial. 2 factorial being replaced by 2 into 1 factorial. So 4 into 3 into 2 into 1 factorial. And then finally 1 factorial is replaced by 4 into 3 into 2 into 1 into 0 factorial. Okay, 0 factorial value is known as 1. So we simply multiply 4 into 3 into 2 into 1, and this will be equivalent to 24. Okay, so this is the recursive definition, and this is how we solve it recursively. Now let's see the algorithm for the same. So procedure factorial, we have to give the input n, which is equivalent to non-negative integer. If n is equal to 0, then return 1. That is, this is your initial condition. This is the initial condition. Else, return n into factorial of n minus 1. This is the recursive condition. Then the output is n factorial. The example is given for the same. Now the next one is recursive exponential algorithm. So over here, recursive exponential algorithm is basically when we are supposed to find a power n. So to find the recursive definition for a power n, we can base a recursive algorithm on the a power n. What can we do? So the initial condition in this case can be, suppose if you want to find a power n plus 1, it is equal to a into a power n, and every time your n should be greater than 0. So this is the recursive definition. This is the recursive definition. While the initial condition, what will be the initial condition? It will be a power 0 is equal to 1. Anything power 0 will be equal to 1. Now to find a power n successively, we have to keep reducing the power or the exponent until it becomes 0. So if you remember, the power is also known as exponent, hence the name exponential algorithm. So over here, we know that we have to keep reducing it till the power becomes 0. Now for this, I don't need to give an example. I believe you can easily understand it since we have already been studying powers from a long time. So over here, we'll just see the algorithm. Procedure power. A is a non-zero real number and n is a non-negative integer. If n is equal to 0, then return 1. That is, a power 0 is 1. Else return a into power of a n minus 1. This is your recursive function. Okay, it again calls this procedure with the power n minus 1. Here it was calling with a comma n. So power of a comma n in the first step. After that, it calls with power of a comma n minus 1. Okay, so each time it will call with the a comma n minus 1, and then you will keep on reducing it until n becomes 0. That is, when your n becomes 0, it will return 1 and your output is a power n. The next algorithm is GCD. So given a recursive algorithm for computing the greatest common divisor of two non-negative integers a and b, with a should always be less than b. So for this, first let's see an example. So we can base a recursive algorithm on the reduction GCD of a comma b. So GCD of a comma b is actually given as GCD of b mod a comma a. Okay, and the condition is that GCD of 0 comma b will be b whenever b is greater than 0. So initial condition is this, and this is your recursive definition. Now for this, we can take an example. Let me take an example with a is equal to 5 and b is equal to 8, and always the condition is that a is less than b. So now over here, GCD of 5 comma 8. We need the GCD of 5 comma 8. So GCD of 5 comma 8 will be GCD of 8 mod 5, so B mod A. So 8 mod 5 comma 5. And we have to keep on doing this until we get 0 in the place of A. So GCD of 8 mod 5 comma 5, 8 mod 5 will give you the remainder 3. So we have to find GCD of 3 comma 5. Now GCD of 3 comma 5 will give you, for this step we will get GCD of 5 mod 3 comma 3. Okay, so B mod A comma A. So 5 mod 3 is giving you the remainder 2. So over here we get GCD of 2 comma 3. Now for GCD of 2 comma 3, I'll write it over here. GCD of 2 comma 3 will give you the GCD of 3 mod 2 comma, we have to write 2 over here. Okay, so 3 mod 2 will give you 1. So this results in GCD of 1 comma 2. Now after that, GCD of 1 comma 2, let me write it over here, that GCD of 1 comma 2 will give you 2 mod 1 comma 1. Now 2 mod 1 comma 1, this will give you 0 then comma 1. So basically we got this initial condition, which is GCD of 0 comma 1, which will be equal to 1. So finally your GCD of 5 comma 8 consequently will be equal to 1, because your final result will, whatever be the GCD over here, it will be your actual answer. So the GCD of 5 comma 8 is 1, as anyway the greatest, there is no divisor apart from 1 which divides both 5 and 8. Okay, so this is the procedure for finding the GCD. Now with respect to the same, we will see the algorithm. So procedure GCD A comma B, non-negative integers, both of them should be positive integers with A less than B. Non-negative, why am I mentioning here? Because non-negative integers even include 0 along with the positive integers. Okay, so here any one of the number can be 0. If A is equal to 0, then return B, else return GCD of B mod A comma A. So this part is your recursive definition, as I have already given, and this is your initial condition, and output is GCD of A comma B, whatever the result over here you get in the initial condition. So for this, I have already solved GCD of 5 comma 8 in the earlier example. You can solve it for any other example. Now next thing is recursive binary search algorithm. So binary search we have already studied in unit 1. So if you remember, I have explained the binary search algorithm, where you divide the array into 2 parts and then you try to find the key which has been given. So if the key is greater than the middle number, you go to the right part, otherwise you go to the left part. The same has been explained over here. And if you remember, the binaries, in the case of binary search, we always try to do it recursively. So this is the binary search example. I'm not going to explain it in detail. You can refer to the video lecture of unit 1. Next, what do you mean by recursion and iteration? A recursive definition expresses the value of a function at a positive integer in terms of the values of the function at smaller integer. Okay, so in the case of recursion, each time you decrease the input value and you try to define your problem with a smaller input. Instead of successively reducing the computation to the evaluation of the function at smaller integer, we can start with the value of the function at one or more integer, which is the base cases, and successively apply the recursive definition to find the value at larger integers. Such a procedure is called iteration. So in the case of iteration or iterative, what we do is we try to take base cases, and from the base cases we try to find the value at for the larger integers. In this case, we were starting from f of 5. In this case, we go from f of 0, we find f of 1, and we keep on continuing with this. So this is iteration. Often, an iterative approach for the evaluation of a recursively defined sequence requires much less computation. So among these two procedures, that is iteration and recursion, iteration is a better procedure, that is it requires lesser computation, so obviously less time complexity. So this is illustrated by the iterative and recursive procedures for Fibonacci number. Now, if you remember what the definition for Fibonacci number is, if the initial condition is f of 0 is equal to 0 and f of 1 is equal to 1, that is your 0th and the first number is 0 and 1, then the f of 2 will be f of 0 plus f of 1. Okay, so this is your initial condition for Fibonacci numbers. Now we will see an example for iteration and recursion with the same. So over here, a recursive algorithm for Fibonacci numbers procedure Fibonacci n is a non-negative integer. If n is equal to 0, then return 0. Else if n is equal to 1, then return 1. Else return Fibonacci of n minus 1 plus Fibonacci of n minus 2. And output is Fibonacci of n. Now, how are we supposed to do this? Suppose if we want to find Fibonacci of 4, f4. Okay. Now, in this case, for f4, what we are supposed to do is we are supposed to take f of 3 plus f of 2. Okay, f of 3 plus f of 2. Now f of 3 plus f of 2, for each of these we need to find f of 3 and f of 2 also. So f of 3 will be f of 2 plus f of 1, while f of 2 will be f of 1 plus f of 0. Now this f of 2 needs to be found out. So f of 2 is equal to again f of 1 plus f of 0. So each time if you notice, even though we have found out f of 2 over here, again we need to find f of 2 for this part where we are getting from f of 3. So we can see that this algorithm requires f of n plus 1 minus 1 additions to find f of n. Okay, so for f of 4 we require 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we require totally nine computations. Out of the 9 computations, these ones f of 1, f of 1, f of 0, and this f of 1 and f of 0 are not needed because they are the initial conditions. So totally out of the 9 we don't require 5, we require 4 computations. Okay, so we can see that the algorithm is the recursive algorithm takes a bit more computation time. Now let's see for the iterative one. So for the iterative one, what we are doing is basically we are initializing the first 0th and the first term to x and y. Okay, so this procedure initializes x as f0 is equal to 0 and y as f1 is equal to 1. When the loop is traversed, the sum of x and y is assigned to an temporary variable or an auxiliary variable z. Then x is assigned to the value. So this uses basically your swapping methodology. Over here we are swapping the values of x and y each time, and what we are doing basically we are changing the values of y to x and z to y, and we keep on adding it. So over here, after going through the loop the first time, it follows that x equals f1 and y equals f2. So in the first loop, what will happen is in this case x is equal to 0, it was f0 and f1. After going through the loop, x will become f1 and y will become f2. So furthermore, after going through the loop n minus 1 times, x will become equivalent to f of n minus 1 and y will be equivalent to f of n. Okay, so you can compute again for f4. You can see that each time we keep on changing it till we run the loop for 3 times. Okay, to get f4 we run the loop for 3 times, and we only require n minus 1 additions. Okay, so this requires far less computation than recursive algorithm. Now the next topic in this recursive algorithms is the merge sort. So merge sort is basically whenever we are splitting a list into 2 sublists of equal length until each sublist has only one element, that is 2 subarrays, and then we keep on splitting it until each of the array has only one element, and after that we merge it in such a way that our list or the array is ordered. Each sublist is represented by a balanced binary tree. At each step, a pair of sublists is successively merged into a list with the elements in increasing order, and the process ends when all the sublists have been merged. The succession of merged list is represented by a binary tree. So use merge sort to put the list 8, 2, 4, 6, 9, 7, 10, 1, 5, 3 in increasing order. So for this, I have the 8, 2, 4, 6, 9, 7, 10, 1, 5, 3. Now, we have to keep splitting the list in such a way that at the end of the split, we need to have only one element in each array. Okay, so let's see that over here, we have to split in such a way that the middle element will be floor value of n by 2. So total we have 10 elements, 10 by 2, 5. So we have to split it at the fifth element. So the list will be in this way: 8, 2, 4, 6, 9, 7, 10, 1, 5, 3. Now 5 by 2, 2.5, and the floor value. So now for this case, m will be equivalent to n by 2, total 5 elements, 5 by 2, 2.5. So if we have to take the floor value, so we have to take the number as 2. So we have to split the list in such a way that we have 8, 2, 4 and then 6, 9. Generally, the condition is that the merge sort is splitted in such a way that the two sublists are of equal length, or one has one more element than the other. So if we have 3 elements in this, we will have 2 elements, or generally, like in the earlier case, both of them were equal. Now in this case, we will have only 6 and 9, while in this case, you will have 8, 2 and 4. You can either take the floor value or even the seal value, because if we take the seal value, suppose in this case we were dividing at 2, if we take the seal value 2.5, we will get 3. So we are dividing it in such a way that the list is divided at the third element. So the general scenario is, the general rule is that the merge sort will have, whenever we are dividing the array, it will have equal length. The two sub arrays will have the equal length, or one of them will have one element more than the other one. Okay, so now over here we will have 7, 10, 1 and then 5, 3. Then 7, 10, 1 and 5 and 3 are separated. 7, 10 and all of them are separated. So we have divided the array in such a way that each of the element is separated. Over here also we will have 8 and 2 separately. Now at the end, when we are supposed to merge it, we have in this way 8, 2 and then we have 7, 10. Along with that, we have over here we divided 4. So when we are merging, we will merge it in such a way that it comes in increasing order. So 2, 8, then 4 is merged with this, so 2, 4, 8, and among 7, 10, we merge 7 and 10. Then it was supposed to be merged with 1, so 1, 7, 10. Then we had 5 and 3 separately over here, and over here we had 6 and 9 separately. So when we are supposed to merge 6 and 9 first, so in this example, the important thing is we have to focus on the recursive nature of this algorithm. So 6 and 9, we can keep the same order. For 5 and 3, we have to change the order to 3 and 5. Next, after that, we will have to merge these two, 2, 4, 8 and 6, 9. So once again, arrange it 2, 4, 6, 8, 9, while this will be arranged as 1, 3, 5, 7, 10. Then finally join it and write it in the correct order. So for this, let's see the diagram a bit clearly. So over here, this diagram is showing you the merging, dividing and the conquering. So merge sort is basically a divide and conquer strategy where we are dividing it first. So 8, 2, 4, 6, 9, 7, 10, 1, 5, 3. It is divided into two arrays, sub-arrays, each of 5 elements. And then again, we are dividing the first sub-array into again 2 more arrays. Again, this is being divided. And this continues till we get a single element in each of the arrays. And once we are done the dividing, we are supposed to merge it in the increasing order. So after that, this is the algorithm. So for the merge sort, first we have to divide the arrays. The arrays will be in this way, L1 and L2, and we keep on dividing it. After that, to merge it, we have another procedure, merge L1, L2, which will be sorted list. And when L1 and L2 both are non-empty, we remove the smaller of the first element and put it at the right end of L. And this continues till we get the merged sorted list. So the complexity will be m plus n minus 1 comparisons are done. This concludes your unit